who think that space telescopes are out floating there amongst the stars, in between them, getting close to planets and getting close-up views, and that's not quite why we put them up there. So I'm gonna move that away from me, and I'm gonna share my thing so I can go ahead and control this. All right, so we're gonna start off with this resource, which you guys have seen before, called ViewSpace, and we're just going to look at one little video that kind of addresses a little bit of what we're talking today with understanding the electromagnetic spectrum. So I'm going to let you guys go ahead and watch this, and I will talk about it once we get through a little bit. And I want you guys to see one more image within here, so I'm going to jump ahead a little bit. So ViewSpace, and I will add, ViewSpace normally has some background music associated with it when it's playing in museums or planetariums. We had to strip it out to share this way today due to some copyright concerns. But in this video, visitors that watch it are able to see the same object in different ways and learn different information about it and get a little bit. And we're going to be doing a little bit of that same thing today. And I want to just share this one resource with you as we move into this today. So we learn about the universe in different ways. What you just saw was light, and I've got a light going through a prism here at the center of the screen, just to give you a visual of that. Light is the oldest way we know to look out into the heavens and find out what is out there. The light that comes from stars, comes from galaxies, comes from everywhere, comes down to Earth, and we're able to see that. There are other ways that NASA uses to take a look at the universe as well now. For example, on the left, we've got an artist's interpretation of gravity waves. You may have heard about LIGO last year and its detection of colliding black holes. On the right, we have an artist's interpretation of cosmic rays coming to the atmosphere and interacting, and we're able to detect those in some ways. There are NASA missions that are detecting all three of these. NASA's involved with LISA, which is a new mission going up to work on gravity waves. Up on the ISS, we have a mission called CREAM, sometimes known as Ice Cream. And that's working on cosmic rays and other pieces of matter that actually come to Earth. But the biggest thing we do is look at light. So what is light? I think most people have seen a rainbow. When you go through school in America, most people spend at least a little bit of time looking at light through a prism, seeing how it's made up of different colors. And if you look at the rainbow, you can see that. And one thing you might notice as you look at a picture of a rainbow or look at an actual rainbow is that how the light kind of fades out as you get to the edges of the red or the edges of the violet, or it at least appears to fade out. It's not actually going away. It's just that our eyes aren't able to detect it. Light is made up of all these different colors, and there are colors that we cannot see. As you get more blue, you're getting higher energy light, and you can go beyond the visible stuff. As you get red, you're getting lower energy light, and you go below that. On the right side of the page, you'll see a picture of William Herschel, who is Carolyn Herschel's brother. He is widely credited with discovering infrared light, which is the first type of light we are aware of that we cannot see. And he was using a thermometer to measure out different types of light, and happened to notice that the light the spot just off where the red light was actually hotter than all of the visible light. So what do we right. So the electromagnetic spectrum is made up of much, much more than visible light and even infrared light. You can see in the middle of this poster here, that tiny little rainbow, that represents the visible portion of all of the light that's out there. You can see how big the infrared right off to its left is in comparison. And if you go off to the side of that, you can see microwaves, you can see radio. These are different types of light. If you go to the right, you'll see the higher energy stuff. You can see ultraviolet, X-ray, gamma ray. And one other thing to take note of in this poster here are all those little squiggly lines coming out of the galaxy up there. Make sure I'm pointing that out there. All of those squiggly lines coming out. The ones on the right tend to have more squiggles, a little more frequent. They've got higher frequency light. The ones on the left have lower frequency. Their the length between the bumps is longer, so we can say that they've got a higher wavelength. And we will have a link to a PDF of this poster available for you guys, either in the slideshow or I believe it's on the Moodle as well. So you can look at this. But why do we care about all of these different types of light? What do they tell us? Well, here on Earth, we can see how different types of light have different properties. For example, in the top left here, you can see what we normally call an X-ray, which is a photograph using X-ray light. X-rays tend to go right through skin, and they're not impeded by it as much as they are by something like bone. So when we take a picture of a hand and let X-rays shine through there, we're able to tell where bones are and where bones are not, if there's a break or something else. On the top right, you see someone with a nasty sunburn. Sunburns are a result of ultraviolet light. And these higher energy light, like X-rays and ultraviolet, can also do things like damage our DNA. They'll actually break the bonds in the DNA, and if that's not repaired, that can lead to things like cancer. Lower energy light gets used for other things. Radio, we think of radio as being a sound thing, but it's actually light. The actual physical machine, the radio, just is able to take that light and turn it into sound waves that we can hear. Microwave ovens are able to cook by shining light on food. The type of light that they have just happens to match up with what makes with the molecular bonds in water, and they happen to excite that and make those particular molecules hot. So these are all different types of light. And they all have different properties, which means that we're able to do different things with them, and we're able to see different things with them. I have another poll question. Mary, if you could pull that up. We'll let you guys go ahead and answer this one. And while that's come, there it is. Sunlight transfers energy to the Earth's surface mostly in the form of, what do you think? Visible light, microwaves, ultraviolet light, radio waves, or all of the above? And while you guys are answering this, I'm also going to let you know that this is one of the most common wrong answers that were received in this poll. I think only 16% of the folks who originally answered this got this correct.
So it's very tricky.
Yes, that's less than random. Any more responses there? Give you just a moment. All right. I think I can end this, and I'm going to share the results. And you guys have picked ultraviolet light and a little bit of all of the above. And like I said, this is a trickier question, and it's not the most intuitive to most people. And on this next slide, you guys will actually see the answer. That most of the light that is coming to, most of the energy from the sun is actually getting to the Earth's surface in the form of visible light. Our atmosphere is able to block the high energy stuff that might come from the sun, the X-rays, the gamma waves, and most of the ultraviolet. There is some ultraviolet that comes through, but most of that energy is in the visible light spectrum. A lot of the infrared gets blocked as well. But the radio is able to get through, but the sun doesn't produce anywhere near as much energy in the radio spectrum as it does in the visible light spectrum. The sun does produce all of these different types of light, but the atmosphere really blocks out a lot of what's coming to the surface, which is why, again, NASA sends telescopes up into space. We need to get beyond that atmosphere so that we can receive that different energy and figure out what that means. Yes, thank you, Mary. The key piece of that question is what's going to the Earth's surface? Sun produces lots of UV, but it is visible light that's actually making it here. So, as I said, NASA wants to learn about the universe, and it uses information from all of the different spectrum. And there are lots of different tools that it uses to get there. And I've got a bunch of the current missions up here. And I have, can I get my pointer here? I've got a bunch of the current stuff, and I've got a few old ones. Integral, Fermi, and Swift are all meant to, the main parts of their mission are to collect gamma information from the gamma ray portion of the spectrum. They may have instruments that go into the X-ray or the UV as well, but they're trying to get information there. New Star, Chandra, and XMM Newton are all missions that are gathering information mostly in the X-ray portion of the spectrum. Galax is no longer active, but that was a UV mission that is more familiar than other UV missions. Now, just about everybody has heard of the Hubble Space Telescope, and it is mostly in the visible light spectrum, but again, this kind of, it's not hard limits the way our eyes have them. The Hubble is able to see a little bit into the ultraviolet, a little bit into the infrared, and we're able to get information from both of those. Now, infrared is where a lot of astronomers are really excited about what's coming. The James Webb Space Telescope, which launches next year, is going to be focused much further into the infrared than Hubble was able to see and get all sorts of information there. Spitzer is currently up there as well. It doesn't quite have the resolving capability that Webb is going to have, but it has given us some really amazing stuff over the years. And Sophia is another interesting one. That's basically a telescope mounted onto an airplane. And it is able to get up above enough of the atmosphere to see some infrared images, and it's a lot cheaper than sending rockets into space. The last two on here, WMAP is an old one, WMAP is an old one that looked at microwaves, and ALMA is not a NASA mission. NASA actually doesn't have any radio missions because radio does get to the ground just fine, so we don't need to send radio telescopes into space. Plus, it would be even more expensive since radio telescopes need to be so big. So as you guys noted, we do have lots of different wavelengths coming from the sun, lots of different portions of the EM spectrum. And you can see all sorts of different images from the sun in this page. These different colors aren't real colors, I should note. The kind of orangish one on the top, HMI continuum, that's the only one that's kind of close to the right color. The only other one that you could actually see in visible light is this yellowish one on the left in 4,500 angstroms. But we use these different colors so that we can differentiate between the different things at a glance. We use particular colors whenever we're talking about a particular portion of what the sun is giving off. We could use black and white for all of them, and that's kind of how the images are seen originally. It's just light or not light, but we need something so that we can see it. Now, those same colors work in everything beyond the sun, everything in the galaxy and beyond. This is a series of pictures of our galaxy, the Milky Way, and you can see all sorts. You can see from radio to X-ray to gamma ray. Optical light is the only one on here you'd be able to see with your own eyes, and you'll see all sorts of different colors used on here. Those colors are not arbitrary. There's generally convention, although it may depend on the type of image. But within any picture, the bluer colors tend to be on one end of the energy scale and the redder colors are on the other end. So what we're going to do next is we're going to take a look at some of the individual wavelengths and get an idea of what sorts of things they can teach us about the universe, what sorts of things we can see out there. So we'll start right off with gamma rays and X-rays. So gamma rays are going to see, we're going to see the very highest energy stuff that there is. Pulsars, quasars, the cores of active galaxies, bursts such as supernovas or high energy collisions. What we have here on the left is a gamma ray map of the universe. This is a picture of the entire sky, and what you're seeing on there mostly are point sources. And this big long streak, this really busy streak across the middle of the image is the Milky Way. But one of the interesting features on here are these kind of red bubbles that are coming off the top and the bottom, and then this coming out of the center of the Milky Way. And that is actually stuff coming out of the supermassive black hole at the center of our galaxy. It was when the black hole fed on stuff in the past, not currently, but in the past, there was some stuff that was ejected that's very hot and giving off gamma ray radiation. So we're able to see where that stuff has come off in the past. On the right, we've got Cassiopeia A, which is a supernova remnant. And this is one thing we can learn a lot about in the X-ray spectrum. X-rays are also great for neutrons and learning about black holes. The actual different colors in here, and I think Kim is going to talk about Cassiopeia A and a little bit more later. But the different colors here are different portions of the X-ray spectrum. They represent different things. For example, the red color on here is actually iron gas or iron plasma. And the green is silicon and magnesium plasma. The blue is titanium plasma. And we're able to figure out where these elements were produced when that supernova was created. And we're able to find out things about how the core of that star that went supernova was kind of sloshing about before that actually happened. Moving on to the ultraviolet and visible stars that we see, we're going to see mostly in the ultraviolet and visible. The ultraviolet are going to show the hotter objects out there, the early and late stage stars. This is the Triangulum galaxy, and mostly the vast bulk of what you're seeing is young star formation. Visible light is what we're most familiar with. All of those gorgeous images, well, not all of them, but most of the gorgeous images that the Hubble Space Telescope sees are going to be in the visible light spectrum. This is that iconic image known as the Pillars of Creation. You can actually see it behind me as well, an older version of that one as well. And this is part of the Eagle Nebula. And what you're actually seeing in this picture are these huge columns or pillars of dust. And inside that dust, there are stars being created. And we can't see those stars directly in visible light, but we're able to tell that they're in there both based on evidence of what's around them and also by looking at other parts of the electromagnetic spectrum. So infrared is one of those things that will tell us. So I'll actually start here on the right. This is a series of 3 pictures of different objects, but they're in different phases of star formation. On the this one that's labeled protostar, the left of the rightmost image, you've got a very early stage star held in a cocoon of dust, and the visible light from that protostar is not able to get out to us. It's stopped by the dust, but the infrared light is able to actually pass through that dust to where we're able to detect it. And as a protostar develops, it gets a little bit hotter. You can see it yellow in this image, and eventually blowing out cavities in the dust and the gas. And we can see those in red here on the rightmost image. And that takes a few million years to happen. But we're able to learn about that because of our use of gathering different parts of the electromagnetic spectrum. But as I mentioned earlier, infrared is a lot bigger than visible light is, the size of that spectrum. And there are different things we can look at when we use different parts of the spectrum. On the left here, we are actually looking at another galaxy, and what you're able to see here is the glowing dust, and this dust is glowing in infrared. Everything from the desk that's in front of me, to the glasses on my face, to the air that's all around us, actually emits some light in the infrared. And if we were able to see in the infrared, we'd be able to see to some degree if we had the right spectrum there. And this dust is heated, and this galaxy here is heated by stars around it, and it actually is we're able to see fine detail in that much easier in the infrared than we can in other parts. Finally, the microwave and the radio. Microwave is produced by cosmic background radiation, among other things. The cosmic microwave background, cosmic microwave background radiation is one of the biggest pieces of evidence in support of the Big Bang Theory. What you're looking at here is another picture of the entire sky, and we're able to see variation in with that microwave background. And what you're basically seeing is the heat from the Big Bang. As the universe has expanded over the billions of years since the Big Bang, the heat has cooled down to about 3 degrees above absolute zero, 3 degrees Kelvin. And now that is in the microwave range for what it emits. And the thank you for the clarifications there, Mary, as well. On the right, we're seeing a picture mostly in radio. That purple light is actually visible light from a Hubble picture, but the radio light there, this is the Boomerang Nebula, we're actually seeing cold molecular gas in radio. This is actually the coldest known object in the universe. It's even cooler than the cosmic microwave background. And radio is going to let us see things like this very, very cold gas. And it also helps us see some high energy events like pulsars and quasars and what they put off. But we're seeing different aspects of them by looking at the radio. All right. So there are a lot of misconceptions about color in many of the images we see. And I'm actually thinking, just based on the timing, that we should turn it over to Kim for a few minutes so that she can talk a little bit about visualizing light, and then we can come back and I'll add on things, since I know Kim is limited in the time she has with us today. So Kim, would you, oh yeah, go ahead, Mary.
Kim, if you can just, I think I've made you a co-host, so you can just click on share screen and you'll kick Tim's screen off and you can share your own slide. I want to introduce everyone to Kim, who is the visualization lead. As you see, she's sharing her screen for the Chandra X-ray Observatory, and she's done a lot of work in thinking about how people perceive color images and how the real data should be visualized. So Kim, take it away. Oh, I remember I muted you. You have to.
Okay.
There we go.
There we go.
About that.
Can you hear me okay? All right, great. Thanks so much for having me. I definitely appreciate it. So we've talked a little bit about the Chandra X-ray Observatory already, and I've worked for Chandra for about about 19 years so far. Chandra was launched back in 1999 and observes the high energy universe of things like exploding stars, air on black holes, colliding galaxies, you know, kind of some really cool stuff, or I should say hot stuff. So I've had the privilege of working for Chandra for a while, and we've talked a little bit about the electromagnetic spectrum already, so I won't spend too much time on it, but this idea that objects in the night sky emit many different kinds of light is really important. And being able to understand and visualize those different kinds of light is also really important for us to better understand our place in the universe. So if there are some musical folks on the line, if we were to, for example, think of someone who plays the piano, and if you played your favorite piece on the piano, but you could only use the middle C key and maybe a few keys around it, how great would your piece on the piano sound? Not that exciting, right? I don't think even chopsticks would sound good that way. So the analogy here is if we could only see the universe with the kinds of light that our eyes can detect, visible light, optical light, it'd be like only being able to access a few of those keys in the grand symphony that is the universe. So being able to observe and visualize information across the electromagnetic spectrum is a really important part of modern astronomy today. And there is so much as far as different kinds of light. It's kind of, you know, it's a great thing to have. It's an embarrassment of riches in a way, but in a really good way. So right now we're looking at our screen on Cassiopeia A, which is supernova remnant, a star that exploded many years ago. And this star was perhaps 15 or so times the size, mass of our sun. And stars, when they age at a certain mass, eventually they collapse on themselves and then explode and disseminate their insides all out into the universe. So we're looking at a remnant now that is about 10 light years across, and a light year is the distance that light travels in a year, so about 10 trillion kilometers, give or take. So this is about 100 trillion kilometers across, give or take. And it's beautiful. This is an optical image from the Hubble Space Telescope, and we're looking at this delicate sort of filamentary structure at around the 10,000 degree mark. Now we can look at that same patch of sky from the Chandra Observatory, and you know, excuse my silly PowerPoints, but essentially death comes alive. So now this star looks completely different. And the best of both worlds is when you take that data and you combine them from multiple wavelengths and you get a multi-wavelength picture of what's going on. However, images of the universe, they really don't start out looking like this and beautiful. They really start out looking a little bit more like this down in the right corner. But this is actually how they really start out. This is essentially binary code, sets of ones and zeros that our computers, our scientific instruments can essentially understand. So when you're looking at an object out in the universe, for example, Cassiopeia A, that we've been talking about, my favorite supernova remnant, the light from that object has been traveling for some amount of time. The Chandra spacecraft in this case, which is pointed towards the object, is then gathering the information on its scientific detectors. It's then stored up and encoded in the form of ones and zeros so that it can be passed down through NASA's Deep Space Network on its way to my laptop, which today is in Providence, Rhode Island. So when we first get that information, we have to use scientific software to essentially tell us what's going on. And by using the scientific software, first we get a table, and the table tells us the position, the X and Y position of each of the photons, each of the packets of energy that struck the detector during the observation. And from there, we use more scientific software to create the visual representation of the object. So as a researcher, as a scientist who's using the scientific software, you can make any number of choices on how to make that image look. And right now we're looking at Cassiopeia A. All the information is called a broadband image because it's all of the X-ray data that we have from the lowest energy X-rays to the highest energy X-rays from Chandra. And we've assigned it to one symbol color. But there are many other different ways to color the universe. So when we look at an image like this, and I've skipped over a few important steps here after we do this translation of information from the binary code to the visual representation. Besides coloring, there's a whole lot that we have to do to it. We have to scale the image, we have to frame it, We have to remove artifacts if there's something in the screen that doesn't belong. Typically with X-ray data, we have to smooth it out. So skipping ahead all those steps, once we get to the point of colorization, we have to make decisions based on what is the story of this object. And in this case with Cassiopeia A, we wanted to kind of show the stretch of the different kinds of energy cuts that Chandra was observing the remnant in. So in this case, kind of like paint by numbers, but in the best sense of that is that we applied red in the lowest energy X-rays, and we applied medium energy X-rays to green, and then finally the highest energy X-rays are in blue. And that color coding, it's kind of like the weather map on the nightly news or on weather.com. The color coding gives you information. But of course, there are a number of things that you need to consider when you do colorization like this. It's often called false color, which sounds like we're doing a bad thing and sitting there with crayons and just having a good time with it. We actually like to use the term called representative color, which seems a little bit less malicious in nature as far as the terminology. But the point is adding color back to the data, adding color that we can't see in this case because our eyes are not sensitive to X-ray light. By adding color in, we're actually adding to the information quotient of the image. Because you can look at a black and white image and you can get some sense of, okay, this is really bright here, kind of dim here, and oh, this is a bright ring here. But once you add the color information, you get a better understanding for what's going on. So now you can see that this red and green material and how it's distributed throughout the remnant is, you know, material left over from the star when it exploded. And then this blue ring around the edge is the accelerating shock. So that color imparts a value. So you can see the individual pieces here on the right of the screen, although they might be tucked behind the videos if you have the videos up. But it's just a way to break down the data. And there are other different ways to apply color to supernova remnants. So I think the version that Tim had up earlier was by chemical composition. And that's also a pretty useful way to be able to break down a data set. So if you can map where the silicon versus the sulfur versus the calcium versus the iron and where it is, well, that tells you something about how the star exploded. So we can also take our data and instead of just look at a flat two-dimensional image, we can see that data changing over time. So in the case of Cassiopeia A, for example, it's a pretty famous object in the nighttime sky, and a lot of observatories have looked at it. It's kind of one of Chandra's signature objects, if you will, because it was one of the very first things that Chandra ever observed. So we've been collecting about 2 million seconds worth of information on this one object, and we can see it changing over time. And when you look at data across time, it gives you yet another value to what you're looking at. And in this case, we're able to essentially understand the velocity of this remnant. And we know that it's traveling, the material on the outer ring is traveling around 11 million miles per hour. So that gives us yet another bit of information. But we can also, using different kinds of light, we can also map it into 3 dimensions. And this was a really exciting thing for us to be able to do. We had to use a basic assumption about the geometry, that it was coming from a single point. And we had to know essentially by using the Doppler effect, we had to be able to map whether the light was traveling away from us or traveling towards us. And we're able to do that using the data from Chandra, but also data from the Spitzer Space Telescope and infrared and optical telescopes on the ground. And so by mapping this data into 3 dimensions, this is the first time that you're ever able to see around, behind, and through a star that exploded 10,000 light years away, 10,000 times 10 trillion kilometers. But yet again, you can see the color here in this case actually goes back to the chemical composition. And the Smithsonian did a slightly different color map on theirs. I believe green is iron in this case. I believe blue is sulfur. And I forget what red is in theirs, but don't quote me on that. You can actually visit the Smithsonian website to learn a little bit more. But we realized we had this really cool format, and this is all free data sets, by the way. So you can take this data and, oh, I forgot about this version. So this, essentially, we took that same data set from the last screen and brought a wire mesh into a software package called Maya that we could then manipulate the colors and textures to make it look a little bit more astronomical. Because the previous data set, we actually had to use medical imaging software that had been adapted for astronomy purposes, which is why it kind of looked like a large spacey brain. So we wanted to make an improvement on that, which is why we took it into this software called Maya and did a slightly looser rendition. I like the previous version better because that's the real data. This is a little bit more mystery and magic tossed in because it's not an exact 1-to-1 ratio pixel to pixel of the real data, but still it's pretty cool to be able to get a sense of how you can see through, behind, and around this star that exploded so far away. But we also wanted to be able to have more of a tactile experience with it. So we used that same three-dimensional data set, and we actually brought it into program to be able to translate it to an STL file to 3D print it. And this model is available on our website for free. You can go to chandra.si.edu/3dprint, and I guess we could probably pop that in the chat box. So if you have access to a 3D printers or any of your constituents do, they can literally hold a dead star in their hands. But by literal, I mean very tiny and in plastic. So, you know, take that for what it is. But I wanted to see if we could push this data set a little further because this is, as I mentioned, my very favorite supernova remnant. So we actually worked with some amazing visualization professionals at Brown University to take that 3D data set and actually translate it into an immersive environment. So this is the first time that we've actually been able to walk inside a dead star. And you can't tell because of the camera angle, but she is actually standing inside of it. So she's able to explore this data set from the inside out. And that's been just a really amazing thing too. We're translating it now from this immersive environment in like a cave-like structure. It's called a yurt. We're translating that now to other types of equipment, including the Oculus Rift. And then it will soon also be available after that for Google Cardboard, which is much more economically approachable. So that's the story of Cassiopeia A, my favorite supernova remnant, and how we get to color it in the universe.
Wow. Well, thanks, Kim. I want to
hopefully that wasn't too much. Sorry.
No, I want to stop and give people a chance to ask you some questions. And I really like that idea of an image having an information quotient, and you kind of calling out all the different channels of information from the three, you know, the different medium, low, high, X-ray energies to the time dimension to the 3D, X, Y, and Z. It's a really neat way to think about conveying information and that there's all these channels of information.
Yeah, I mean, it's all a big process of translation, right? So these images, they don't exist as these giant selfies in the sky, right? We have to have people involved in the process of translating that information to a visualization, you know, that tells a specific story. So these examples are all the same story and they're all the real data. They just express the data in a different way for the specific audience. And that's kind of the amazing thing about having a job like this, is that you can work with the same data set for so long and still find new ways to understand it and enjoy it. And they have a purpose too. The three-dimensional modeling, for example, that actually helps scientists to model supernova remnants for a living. And yes, that's a job. It actually helps them understand their data sets differently. So they need to model it essentially in two phases, which means, yes, there is this sort of spherical explosion that goes first, but then there is this secondary eruption that kind of comes out more in these fiducial types of jets. So that information then feeds back to the researchers again, and, you know, yet new things are discovered and understood.
Yeah, so I see that we haven't got any questions in the chat box. I want to encourage people, if you're more comfortable just asking Kim or making a comment. I know we have some folks from art and design museums who might be interested in thinking about presenting, you know, some of these ideas in terms of interpreting data for the public visually. So I'm going to give you some wait time here.
Sure. If I could hum, I'd hum the Jeopardy theme song right now.
Well, we Kim, we have an online kind of community of practice where sometimes questions come up later. So if any come up, we'll come back to you and get some answers. And we will also, we have someone very interested in using the 3D print models for their students.
Yeah, so did anyone put the URL in the chat box? If not, I can try to do that really quick. Where's my chat box?
I misspelled it. It's chandra.si.edu/3D print.
Yep, that's it.
Yeah.
Yep.
So, yeah, and we will have those in our resource section on the community of practice. So everybody can look for that as well. And that's actually a really great way of potentially putting a program together, understanding the universe in 3D, understanding it in color, using these things. So
yeah, so 3D printed models have been really popular with various kinds of audiences, from school children to the blind and visually impaired. We've taken a lot of notes from that community to understand how they explore the material tactilely, and that includes having a version of Cascade that's cut in half, so you can explore it from the inside out as well. So there are a lot of tips like that. If anyone's interested in talking about how you do 3D printing for different kinds of audiences, please get in touch. I'm sure my email is somewhere over here on the screens, one of the screens that they had up, but please don't hesitate to ask.
Find that somewhere here. Kim, we had, I don't know where your email went. Sorry about that. We'll put it in the chat box.
Sure.
We had a question from Carrie Carrata. Is there a table that students can use to determine what the star is made of by the colors they represent? Like,
is there a table, meaning like just a simple chart? We actually did have a very simplified chart at some point for one of our handouts. I could look up and see where that is and email that around. It was simplified because there's a lot of overlap. It's not like a perfect clear cut, iron is here and silicon is here exactly. But we did have a simplified chart I could try to find. Okay. It was like averaged out by pixels and all that kind of nonsense. So, but that might be useful if I'm understanding the question right.
And then here's an interesting question. Is it possible that there are energies or wavelengths that we have not yet discovered?
Yeah, I've gotten that question. I've gotten that question before, and I'll let Tim talk about more because he's more the expert in that. But you know, I'd love to think so, but for most of the people I've talked to, they often say probably not. But with that, I guess to give it back to Tim. And if there's no more questions for me, I have a conference I need to get back to.
Okay, thank you so much, Kim.
Thank you. Bye, everybody.
That was great. So, Brandon, I don't know if you want to take us the question about, in terms of wavelengths that we don't know about, that's probably not true, but wavelengths that we haven't got detectors to see what's coming out of the universe, that might be the case.
That is a very interesting question. All I can say to that is that, you know, if there are missing places in the EM spectrum, it's because it is a spectrum, it's a continuum. It's going to be either higher energy than gamma rays or lower energy than we have so far located on the radio regime. And there are limits to the physical universe as we understand it to what can create those high energies and the highest possible energies, and limits to what create those lower energy radio waves. So I don't have a good answer for, is it possible that there could be some event out there that could possibly create something that's really high energy? You know, the highest energy event we know about in the universe is the Big Bang. And we don't have any, you know, we look at that now through microwave because it's cooled down over the 14 billion years or so. But, you know, that's a good question. We can ponder that more and give a more complete answer on the Moodle after we think about a good way to answer that.
Great. Okay, well, I'm gonna wrap us up by highlighting a few resources, and then Eric will bring us through next steps, resources that are related to this whole topic of the understanding the universe across the spectrum. And of course, Tim already highlighted ViewSpace. Tim, just for time, I may actually not show this whole video of this particular ViewSpace module. But again, ViewSpace has these updated modules from Space Telescope, many of which highlight the information coming from the NASA Great Observatories. Another resource that we've spoken about before is the AstroPix website, and that's really a great place to search for images of the same object across different wavelengths, or images that represent the electromagnetic spectrum. Here's an image of a galaxy M81, but you can see this is one of these multi-wavelength composite representative images. And the nice thing I like about AstroPix is you can see down here, they tell you for this image what wavelengths have been represented with what colors. So here's an image that in which all the, Hubble itself probably has a gorgeous 3-color image of M81, but in this image, all of the Hubble information is only represented in green, while all the infrared information from Spitzer telescope is in red. UV information from the GALEX satellite is represented in this purple, and X-ray information, which really highlights the center of this galaxy and all these hot spots that might be active black holes swallowing up the stuff around them, is in blue. So AstroPix is always a nice resource. Another resource is the web, this webtelescope.org/infrared site. And I'm actually going to bring it into view here and show you, because it has some really nice features. It has an interactive interface on the website itself. So I picked the infrared world category here. Is there a problem?
I can't see what you're showing.
You can't see what I'm showing.
We're seeing the PowerPoint right now.
Okay, you're seeing the PowerPoint. Are you seeing the web telescope on?
But not.
Ah, okay. So hang on. Let me do a new share and do desktop 2. All right, let's try that again. There we go. All right, sorry about that. Didn't do that right. So James Webb, oh, I didn't get it. Infrared site allows you to, has this nice interactive feature. So if I click on infrared world, this image is the optical image of what looks like a basement. But if you happen to have infrared eyes or an infrared detector, okay, here's the same image as seen by a thermal camera that sees infrared. Another image that shows features like that. If we look at the galaxies, and I look at this Andromeda galaxy, here's a typical view of the Andromeda galaxy. Everybody's familiar with, if you're familiar with a galaxy, you might be familiar with the Andromeda galaxy. And this is an optical, and you see all these dark dust lanes. But when you look when you have an image that has more infrared information rather than less information, those dark dust lanes turn bright because the dust itself actually emits infrared. It blocks optical, but it emits infrared. And so I really like this little slider feature here. So that's a neat resource. I'm going to pull that out of the way. And the next resource that many of you are familiar with is Micro Observatory, from those of you who participated in the Youth Capture the Colorful Cosmos project. But I did want to show you, and Micro Observatory allows you to use our small robotic telescopes to take images using red, green, and blue filters, so you can create 3-color images of many objects in the sky. But we also have a new image processor that I kind of wanted to do a quick demo with, which is in this Analyze Image tab. And once you take an image using the Micro Observatory interface, you can open it after you download it from your email. But I wanted to show you that in our archived images section, down at the bottom, we have a series of NASA FITS images. And in fact, that CAS-A image that both Tim and Kim talked about, we have the actual original raw data in low 0.5 K 1,000 electron volts, medium 1.5 kilo electron volts. This is how you call X-ray energies, and high energy. So if I open the low energy CAS-A, and I don't know, I use the slider and bring out that, and I colorize, whoops, sorry about that. And I colorize that red. And then I open the medium energy CAS-A X-ray data, and I enhance that and color that. It's medium, so I'll color that green, just like visible light of medium energy is green. And then I open up the high energy CAS-A, and this is really, there's very few photons here, so it's much crazier there. And I'll make that blue, and then we'll do RGB mode, and you can get your own 3-color image of the CAS-A using the real data. So we'll in this archived image, we'll be adding other images to explore the electromagnetic spectrum, including some Hubble images. I have them on my desktop, and I don't have time to demonstrate them at the moment, but I wanted you to know that this is a new resource to compare your own Micro Observatory data to NASA multi-wavelength data. And then finally, let's see here, what's the last resource? Oh, the Chandra website itself has a photo album. Here it is, where again, and here's that Crab Nebula that Tim showed earlier, and there's a lot of information in their multi-wavelength photo album where you can compare different wavelengths of the same object and then view the composite. Kind of amazing to me, the difference between the X-ray view of that pulsar in the middle and the optical, the kind of composite view of all those filaments of this exploded star. And then one more, the last but not least resource that I wanted to highlight today is kind of a fun series of videos from our colleagues at the Spitzer Space Telescope Center. They've created this cool Cosmos IR-relevant astronomy, irrelevant astronomy, IR-relevant astronomy. And this video, where is it? Oh, yes, Spitzer Space Telescope, the musical. I think I've set this up so that you'll hear the music when I play it, but let's find out. I'll just play the first half minute of it because it's kind of fun. But it's a description of why we need a telescope that sees infrared. And here we are.
Hey, it's the filmmakers. How's the documentary coming?
You know, I'll be honest with you. I don't understand this whole Spitzer Space Telescope thing. Doesn't NASA have enough telescopes already? Infrared. Is that like pink?
Since you're making a documentary about Spitzer, it might be a good idea for you to know what Spitzer actually does. You see, Spitzer was launched in 2003, the fourth of NASA's great observatories, on an Earth trail in orbit with its back to the sun, 3 eyes to the sky with coolant for one. It's 6.
Mary, we can't hear you.
I'll stop there with the irrelevant and irreverent astronomy as a resource. The jingle's going to be stuck. Yeah, my head too, Patty. So with that highlighting of resources, Erica, why don't you go through next steps and I can advance for you. Why don't we do it that way?
All right.
Next steps for our little community of practice.
All right. Just to see where we are now, we've now made it through our 3rd webinar on a good path here to understanding the universe. So today we finished up how does the universe work. In 2 weeks, we're going to begin with how did we get here. Next slide.
Oh, yeah.
All right. So today, like I just said, finished understanding the electromagnetic spectrum. We have a little bit of homework. Hopefully you'll participate. We love hearing from you. Contribute to our weekly discussion topic. We really want to hear from you, especially some of our art people that hopefully have some of their own tactics on how you can apply visual thinking and other strategies to astronomy. So as we said, there's a lot of information in these pictures. They're beautiful, but there's also lots of information. So what kinds of strategies do you guys use for looking at images?
Yeah, and actually strategies from the art education world would be great to know about.
We would love to hear kind of what you do at your own institution. So please contribute to that conversation. We'll be posting that later today. And then we still want to hear from you about what resources you're finding and engaging in, and let other people know what ones you're working on. So we have a forum under the Affiliations forum talking about all the resources, what's working for you. Then 2 weeks, we're coming back to webinar number 4. Looking out is looking back in time. Sorry, I'm looking at Mary's screen.
Yeah, and Brandon will be hosting that. And then finally, Patty, I just wondered if you wanted to say something to let people know that we'd be hosting a little meeting at the conference for those who are there. I've unmuted you.
So in the next upcoming days, we're just working out the information, but for those attending the affiliates conference and from October 2nd through the 4th, we're going to have a little table there. It's called for Birds of a Feather on Tuesday. So come and talk to us, and we can, come with your ideas for your projects. We would love to hear from you of how we can help you in any way, and the sort of resources that work best for your institution. So, I'm going to type in my email here, and just let me know if you have any questions.